is going to be the first in a series of, well, I'm not quite sure how many videos about a certain very important model in differential equations. The shortest name that you can give for the model is the model of the harmonic oscillator. You can add all sorts of descriptors to this. You can talk about something called the damped harmonic oscillator. You can talk about the forced harmonic oscillator. You can talk about the damped forced harmonic oscillator, so it's both damped and forced. There are lots of different variations on the harmonic oscillator, but we'll start with just the basic model, and we will gradually work our way up toward more complicated models. What sections in the book does this cover? Well, there's a bit about the harmonic oscillator in section 2.1. It also comes into play in section 2.2 and 2.3. Later on in chapter 3, you'll read about the harmonic oscillator all through chapter 3, with a special focus on section 3.6 and 3.7. Then chapter 4 also comes back and focuses on the harmonic oscillator in much more detail, in particular the forced case. But let's start basic. So this is something you would want to watch certainly as you're reading through section 2.1 and 2.2, and perhaps even 2.3. What is the harmonic oscillator? Well, the easiest way to imagine a harmonic oscillator model is to imagine a wall, a very solid wall, over on the left here, a floor that is made out of not just ordinary ice, but extra slippery ice. It's got no friction. We're going to pretend it has no friction. And we've got a mass, a block of wood maybe, sitting on top of that ice and attached to the wall with a spring. And in this picture, we might initially assume that mass is at rest. And think of this horizontal position of the mass as the rest position and call it 0. It would make the most sense to label the horizontal axis with an X, since that's what mathematicians and scientists usually do. But to stay consistent with our book, which focuses on the dependent variable typically as being y, I will label the horizontal axis with y. And y equals 0 essentially is the center of mass of that block of wood. That'll be y equals 0. If we just leave the mass there at equilibrium, where it's not moving, it will continue to not move. Of course, what's more interesting is to imagine that we pull the mass away from the wall, or that we push the mass toward the wall and then let go. Or maybe we give it an initial push even from equilibrium, one way or the other. That's going to set the mass in motion. And you might imagine that if I do such a thing, and if this really is very slippery ice, so that it effectively has no friction with the mass, and if you also imagine that this spring is ideal in the sense that there's no internal friction, then the mass will oscillate back and forth infinitely often, forever and ever. And if there really is no friction, I guess I have to assume there's no air friction either, so we're in a vacuum, it will oscillate with the same amplitude forever and ever. That's what the model predicts, at least. Of course, in reality, there's friction. You would have internal friction from the spring. You'd have air friction if you weren't in a vacuum. And even ice does have a little bit of friction associated with it. So there are all sorts of frictional forces that tend to damp this harmonic oscillator. But to keep it simple, we assume that there are no damping forces initially. We need to know a little physics. The first fundamental principle that we need to know here is the equation that comes from Newton's second law, typically written as F equals ma. M is the mass of the object, a is its acceleration, and F is the force on the object. In the context of this drawing that I have here, y being a measure of the position of the object, and the object is only going to move back and forth horizontally, the acceleration is really the second derivative of y with respect to time. Y is going to measure, y is not just a label for this axis here, y is also going to measure the position of the mass. And if the mass moves, it will be a function of time. The derivative of y with respect to time will give you the velocity. If the object is moving to the right, it will be a positive velocity. If the object is moving to the left, it will be a negative velocity. And its second derivative, the derivative of velocity, the rate of change of velocity, is called acceleration. That's telling you how fast the velocity is changing. I could also write it like this: m times dv dt, where v is dy dt. V the velocity, y the position. Acceleration is going to be positive when the velocity is increasing. Now, there's two ways that can happen. If the mass is moving toward the right and increasing its speed as it moves toward the right, then the acceleration, the velocity is increasing and the acceleration is positive. There's another way the velocity can be increasing. That's if it's moving to the left and slowing down. If the mass is moving to the left, its velocity is negative because it's moving to the left. But because it's slowing down, that velocity is actually increasing towards zero, because velocity is assigned speed, S-I-G-N-E-D. Speed is the absolute value of velocity. Velocity is positive when it moves to the right and negative when it moves to the left. So if it's moving to the left, it's got a negative velocity. If it's also slowing down, the velocity is actually increasing, and the acceleration would be positive. Two ways to have a negative acceleration: if you're moving to the left and speeding up, that's a negative acceleration, or if you're moving to the right and slowing down. Those are both negative accelerations. The velocity is decreasing. So that's one fundamental equation we need, that the force is the mass times the second derivative of the position with respect to time. And there are units involved, of course, with these things. Y would typically be measured in meters, time in seconds, and so this second derivative, this acceleration, would be in meters per second, abbreviated meters per second squared. The mass is in kilograms. And the force, well, you might say its units would be kilograms times meters per second squared, but that's equivalent to newtons, is the shorthand name that scientists give to force. So that's one key fundamental fact. This fact is true no matter what kind of forces are acting on the object. With a mass on a spring, however, so this is Newton's second law, I'll label as Newton 2. With a mass on a spring like this with no other forces besides what's called the restoring force of the spring, the force has a particular form. That's given by something called Hooke's law. There could be other forces like friction, and, well, gravity is actually acting on the mass too, but there's also the opposite force from the ice pushing upward against gravity that's keeping the mass from moving up and down, so we can ignore the force of gravity. We only think about the restoring force of the spring. What is the restoring force of the spring? Well, it's a tendency to push back, in a sense. If you pull, or pull back, if you pull the mass away from the wall, the spring wants to pull the mass back toward the wall. You feel that tension when you hold it there. You have to hold it with a certain force to keep it in place. When you push the mass toward the wall, the restoring force wants to push it away from the wall. So the first fundamental thing to realize about Hooke's law is that it points in the opposite direction as the value of y. If y is positive, the restoring force is negative. It wants to pull back toward negative values of y. And if y is negative, if the spring is scrunched, then it wants to push away the restoring forces in the positive direction. So we need some quantity that expresses the restoring force in terms of y, and is negative when y is positive, and positive when y is negative. Certainly, if I wrote down negative y here, that would be something that works. But to account for the possibility of having stiffer or looser springs, something real hard and stiff versus something loose like a slinky, we want to have another constant involved, a constant of proportionality, really. We'll write the restoring force like this, as negative k times y, where k is actually a positive constant. K will not change. This is really an assumption. That's what you do with modeling, is you make assumptions, and then you hope that your assumptions, especially if you keep them simple like this, are true. Whether or not they really are true is something that you have to verify with experiments. Experiments have verified that Hooke's law is a pretty good model in situations like this, as long as you don't stretch the spring too far to get it close to a breaking point, or I suppose smush it too far to get it close to some kind of breaking point. This turns out to be a pretty good model. There are other models you could try that satisfy the property that the force is negative when y is positive and positive when y is negative, like ky cubed, negative ky cubed. But in modeling, you want to keep things as simple as you possibly can get away with. So we try something real simple and see how well it works. So what we do now is we combine these two facts, these two models in a sense, and equate those F's, equate those forces to get the following equation. M times the second derivative of y with respect to t, the acceleration, equals negative ky. And what we realize here is that since y is a function of t, is that we really have a differential equation. It's a differential equation in the unknown function y, which is a function of t. Y is the dependent variable, t is the independent variable. It's second order. You've got a second derivative involved. It would also be second order if we, in addition, had a first derivative involved, though in this particular case you see that there is no first derivative. It would still be second order as long as that second derivative is involved. It also turns out to be a linear second order equation. I won't go into why at the moment, but it turns out that if you have two solutions to this equation and you add them or multiply them by constants or form a general linear combination, that you will get another solution to this equation. What should we do with this right now, right off the bat? Well, I would like to go ahead and try to solve it. Turns out to be a good idea to perhaps divide both sides by the mass m. And for the sake of simplicity, replace k over m with another letter, like q. lights just went out. Well, let's try to continue anyway. I guess you don't really need to see me real well. I think we'll try to continue with it as is anyway. So there is a simplified form of the differential equation. I'm going to use the time-honored method of guessing. We've done a little guessing already with first-order equations in Chapter 1. Let's guess here also. The issue is with guessing is, how do we go about guessing? And sometimes it's easy and sometimes it's not. This is relatively easy to guess an answer to if you think about it. We're looking for a function whose second derivative is a negative constant times the function itself. Think about that for a minute. What functions do you know of? Let's pretend the constant is 1 for the moment, or -1 for the negative constant. What function do you know whose second derivative is the opposite of the function itself? A little bit of thought should help you remember that cosine and sine are two functions whose second derivatives are the opposite of themselves. Sine of t has a derivative of cosine of t, and then therefore a second derivative of negative sine of t. And cosine of t has a derivative of negative sine of t, and then a second derivative of negative cosine of t. So both of those functions would satisfy this equation if the q were 1, and so the negative q were -1. With this negative q in here, it's a little trickier. But if you do a little experimentation and guess functions like cosine of some constant times t, through a little experimentation, you'll realize the constant square root of q will work. And you can check that out. The chain rule is going to be what allows it to work. When you take the derivative of this, y prime will be negative square root of q sine of square root of qt. And q is positive here since it's k over m, and those are both positive. And the second derivative, I'm going to get another factor of square root of q, giving me negative q. Cosine of square root of qt. Negative q times the original function. Y equals sine of square root of qt also will work for the same kind of reason. The chain rule applied twice because we're taking two derivatives will allow us to see that sine of square root of q times t does solve this equation. Turns out that with second order equations, if you've got two functions which are not multiples of each other, like this, and both solve the differential equation, that an arbitrary linear combination of them will be the general solution. K1, it'll be my first arbitrary constant, times the first function, cosine of square root of qt, plus K2 times sine of square root of qt. My general solution is going to be a linear combination of my two solutions that I already found that are not multiples of each other. You do need two solutions like this to combine with a linear combination where you're multiplying them by arbitrary constants and adding the result to get the general solution of a second order linear equation like this. As the general solution, you can use it to solve initial value problems. Now, initial value problems for second order equations require two initial values. You need an initial value for the function itself, typically at t equals 0. And, well, there are other kinds of initial values you could consider, but typically you also consider an initial value for the derivative of the function at t equals 0. That's the most typical way initial value problems are stated. If we think about it in the context of a mass and a spring, like this, we might imagine pulling the mass say, 1 meter away. Imagine this is a pretty big mass and a pretty big spring. Pull it 1 meter away, so the initial value of y is 1. And if we let it go from rest, the initial value for y prime, which is the velocity, will be 0. So that would be a pretty typical kind of initial value problem, to add the conditions that y of 0 is 1 and y prime of 0 is 0. These two initial values will allow us to solve for the unknown constants. The fact that y of 0 is 1 means that 1 equals k1 cosine of 0 plus k2 sine of 0. We know that cosine of 0 is 1 and sine of 0 is 0, and therefore k1 must be 1. If I take the derivative of y to get y prime, from the chain rule I'll get negative k1 square root of q sine square root of qt, and then a plus k2 square root of q cosine of square root of qt. Just differentiating y. Plug in t equals 0 and set the result equal to 0. So I'm setting y prime equal to 0, and I'm also setting t equal to 0. That's 0, this is 1, and so the resulting equation is that k2 times square root of q must be 0, and therefore k2 must be 0. Q is not going to be 0 here. Q is k over m. M is the mass, it's definitely positive. K is the spring constant. It's positive, otherwise we wouldn't have a spring. It would be a non-springy spring. It would be non-existent. So Q is definitely positive. K2 is required to be 0 here. With K1 equaling 1 and K2 equaling 0, we see that the particular solution to this initial value problem is y equals cosine of square root of qt. In the time we have remaining for this particular video, I want to show you another perspective on this problem. The system perspective. Although, very briefly, I suppose we should think about graphing this solution, y as a function of t. A regular ordinary cosine graph, though its period and frequency would be different than the ordinary cosine graph. Its amplitude is 1. The period, which people typically call a capital T, is going to be 2 pi divided by the multiplier of the little t, square root of q. If q is large, that's going to be a small period, which would be high frequency. There would not be very much distance between the peaks. The period is the distance between the peaks, sometimes also called the wavelength. The frequency is the reciprocal of the period, square root of q over 2 pi. So once again, if q is large, meaning if the spring constant k is large, then the oscillation is going to be very fast. The period will be small, and the frequency will be large. On the other hand, if q is small, corresponding for a fixed mass to a small k, then t will be large, and the frequency relatively small. So stiff springs, where k is large, oscillate faster, and looser springs oscillate more slowly. What is the system perspective? We can always convert second-order equations like this to systems, a system of 2 first-order equations. Essentially what you do is you introduce a new variable, v, which is the derivative of y with respect to t. It will be the velocity. That new variable equation, that defining equation for v, will be one of the equations in your system. The other equation is obtained from differentiating both sides of this one. dv dt is the second derivative of y with respect to t, which we already know is negative q times y. So the resulting system that you get, if we put the derivatives on the left-hand side, dy dt equals v is the first equation in your system, and dv dt equals negative qy. As a system, we will eventually see that we can think of this, well, it's a linear system, we'll be able to think of it in what's called matrix form. We'll be able to draw the vector field for this system in a phase plane. It'll be a YV plane with y horizontal and v vertical. And, well, if we think about the particular solution we found from that initial value problem, y equals cosine of square root of qt, we can find v for that particular y and get negative square root of q times sine of square root of qt. And then we can take these two equations, these parametric equations, which are solutions to the system, and by the way, you can check that it solves the system. The fact that dy dt is v is obvious, and the fact that dv dt is negative q times y is pretty quick to check too. These parametric equations will generate what's called a parametric curve. And we'll sometimes use what's called vector notation, capital Y vector of t, where I'm putting these two solutions into an ordered pair, which sometimes we might write horizontally, sometimes we might write vertically as a column vector. And as far as graphing it, we think of it as being a point that gets traced out as t changes. Think about what happens here as t changes. When t is 0, y is 1, and v is 0. We're at the point 1, 0. As t increases, y will decrease. And v will also decrease. Y will decrease from 1 down towards 0. And v will decrease from 0 down towards, well, it'll be a minimum of negative square root of q. So what we're going to get is a parametric curve in the plane like this. It'll have a minimum for v of negative square root of q, and this was y equals 1 right there. And it will end up continuing like this. You can think about how y and v continue to change. And this is a periodic function, so it's going to come back to itself. And it's also possible to prove that this curve is lying on an ellipse with a semi-major axis of square root of q and a semi-minor, well, q is bigger than 1 at least, and a semi-minor axis of 1 if q is bigger than 1. That's the parametric curve. That's the solution curve in the phase plane that this particular solution will generate. And there's an intimate connection between these two perspectives. To end, I just want to quickly show you on the computer how to graph that with our CD-ROM that comes with the book. Mass spring is the most basic option here, the most basic simulation we can run that will simulate a mass and a spring. We're considering the undamped case, which this is automatically set for. B here will measure damping. We'll talk about that in future videos. M is the mass, K is the spring constant. The B is set at 0. What we're looking at here is a direction field, which is a renormalized vector field. We're making all the vector lengths smaller, and in fact it looks like we're making them all the same length here. I'm going to, well, the y and the v axis are different than what I had. That's maybe a little unfortunate, but you should realize I think the reason it's done here is so that y can measure the up and down motion of this spring. The effect of gravity has already been taken into account in a sense, so we still can ignore gravity. And let's try an initial condition of y equals 1 and v equals 0. There we go. And this particular graph goes around counterclockwise, whereas my graph went around clockwise. M and K are both set to 1 here, so Q would actually be 1, square root of Q would be 1, and the V-intercepts would be also negative 1 and 1. And you see a cosine graph. We're seeing the graph of the position. You also can choose to graph the velocity. Which is the derivative of cosine of t in this case, and negative sine of t is the blue one. Though that's harder to see in the picture, how that velocity is. But you should try it. When the blue curve is positive, the mass is going up. When the blue curve is negative, the mass is going downward. When the red curve is above the axis, the mass is above its equilibrium. And when the red curve is below the t-axis, the mass is below its equilibrium. Finally, to get you in the mood for thinking about lots of videos about mathematical modeling and thinking about it on your own, I've got a quote from Paradise Lost by John Milton. I'm not really a poet. I'm not very good at reading poetry, but I'll do my best here. It's kind of a nice thing to think about in terms of imagining us humans as trying to model the universe, and who are we to model the universe, to think that we can do it. But it's kind of amazing that we can. It says, from man or angel, the great architect did wisely to conceal and not divulge his secrets, to be scanned by them who ought rather admire, or if they list to try conjecture, he his fabric of the heavens hath left to their disputes, perhaps to move his laughter at their quaint opinions wide hereafter. When they come to model heaven and calculate the stars, how they will wield the mighty frame, how build, unbuild, contrive, to save appearances, how gird the sphere with centric and eccentric scribbled o'er, cycle and epicycle, orb in orb. One of the future models that I would like to look at, although it's going to be a low priority for me at the moment, is modeling motion of planets in the solar system and satellites that we might happen to send out. Not sure how much time at this point I'll have to put into those videos, but maybe by the time you're watching this, I've already done that. And that can especially inspire you if you know what cycles and epicycles are historically and think about modeling the motion of the planets. It could be something that's really fun, and I'm looking forward to doing it eventually. I guess I better leave the light on so that we can turn it off.